Good afternoon and welcome to our live streamed tour of the universe from the California Academy of Sciences. Thanks for joining us here on Facebook or YouTube or whatever your preferred platform. My name is Ryan Wyatt. I'm the Senior Director of Morrison Planetarium and Science Visualization at the Academy, and I'll be your host for the next half hour, taking you from low Earth orbit out to the edge of the universe. We're starting here at the International Space Station, my favorite place to start this tour because it's a nice human scale. If you can imagine from one end to the other, from the left to the right, it's about the size of like a football field, whether you're playing soccer or American football. And people are actually on board. Right now, there are a couple of people who are stuck there longer than they'd hoped to be. But the idea is that within these little sort of canisters here, you can imagine astronauts at work. And this is as far as humans travel into space these days. That's why I like to start here. But in the show that we're about to see, we're going to travel much, much farther. Because we're not limited by putting up nuts and bolts spacecraft. We are not limited by even the speed of light. Instead, we can travel through a virtual model of the universe constructed using the latest data from everything from NASA probes to astronomical observations. And this accurate 3D model is actually being displayed using free open source software called OpenSpace. And we'll be sharing links to that in the chat. But what I'd like to do is sort of tell you a story using the software. We're going to pull away from our International Space Station. It kind of looks like it's plummeting into the ocean there. That's not the case. What's happening is that we're pulling away from its location. So it appears to be getting smaller in frame. I'm actually going to bring up a line that represents the trajectory of the International Space Station around Earth. That gives you a little sense of the dimensionality here. As we pull farther away, you'll start to see Earth recede as well. But the International Space Station is really quite close to Earth's surface. In the scheme of things, it's a few hundred kilometers above Earth. Again, as far as anyone travels into space these days, although there are plans to travel much farther like we once did. And as we pull far enough away, we're going to see that bathymetry of the ocean, the ocean the sort of ocean floor, be replaced by a very recent but day-old collection of images of Earth's atmosphere. You'll notice here at the bottom of the screen, there's kind of a seam, a hard edge to some of the clouds, and that's because what we're doing is actually integrating real-time or near real-time data from NASA satellites to be able to show you what Earth looks like right now. So we're kind of nowhere near California at the moment. In fact, we can see at the pole of Earth here, there are some jagged edges to the data there as well. And that's because there's not enough illumination at this time of year for the spacecraft that sends us these images to take pictures of that part of Earth. So this view of Earth is pieced together using the latest imagery that we have of Earth. So we could actually spend a lot of time talking just about Earth, but this is a tour of the universe. So we want to take you much farther from home. And to do that, we're going to go ahead and pull away from our location around Earth and begin to explore our solar system and eventually the stars and galaxies beyond. So as we begin to pull away from Earth, I'll actually go ahead and fade up some orbits for, first of all, this trajectory of Earth around the sun. So that line connecting the bottom of the image to Earth is actually Earth's orbit around the sun. But here, this kind of incomplete circle that you see around Earth is actually the orbit of Earth's moon around us, around Earth. And if you can imagine this distance, and the moon is here at the bright end of this tail, that's as far as humans have ever traveled out into space. Now, this is a little abstract, but basically, the distance from Earth to the moon is about 400,000 kilometers, 240,000 miles. And although that's a really long distance from in human terms, it's like if you could imagine if you had a car for a really long time and you drove it every day and drove it quite a ways, you might put 200,000 miles on it. That distance was traversed by astronauts back in the late 60s and early 70s in a matter of days, and light actually traverses that distance in about a second and a half. So takes light about a second and a half to travel from Earth to the moon or vice versa. And that concept of light travel time is something that we'll come back to during the show. Kind of disappearing off the top edge of the screen there, you can see this orange dot that represents our sun. And this tangle of lines that you can see represents the plane of our solar system. The orbits of all the planets lie in roughly the same plane. And that means that when we look at them edge on, we see this kind of tangle of lines that crisscrosses through the screen from the kind of lower left to upper right. Now, the sun is about 8 light minutes away, which means it takes light about 8 minutes to travel from Earth to the sun. So let's actually keep pulling away from Earth, but change our orientation a bit so that we can see the sun and the orbits from a little bit different, a little bit easier to understand perspective. So let's go ahead and rapidly pull away from Earth so it appears as less than a pixel on our screen, and then tilt up, or actually fly up above the plane of the solar system so that we can see the orbits of those planets maybe in a little bit more familiar kind of context. Because this is the sort of illustration that you might have seen for the solar system quite frequently. These orbits of the planets around the sun. In here closest to the sun, we have Mercury, then Venus, Earth, and Mars. So right now, you can see the orbits of just the 4 inner planets in our solar system. These are also called the terrestrial planets. They're Earth-like planets. If you can imagine visiting Mars, like some of our spacecraft have done, it's a planet that actually sometimes looks remarkably like Earth, the desert environment of Earth. It is a world with a solid surface, so we can touch down and take a look at what's going on there. Now, the other planets, and so now we've moved out farther from the sun, so we can see the orbits of Jupiter, Saturn, and now, as we move farther away, Uranus and Neptune's orbits come into view. Those 4 planets are much different. They're giant planets. They're planets that are sometimes called gas giants, but they're really just large, less dense planets. They're not rocky. They may have rocky cores, but they're not as dense as the terrestrial planets, but they're much bigger. And I think we might have enough time to actually go ahead and pay a visit to one of those. So let's go ahead. And to do this, I'm going to actually expose some of the controls here to show you how we can make our journey to a specific location in the solar system. And so I'm actually pulling up the controls that you can use, again, from home using this free software. And I know that people tend to like Saturn. And actually, I should note that because this is a live broadcast, if you have questions and just want to ask questions in the course of the show, please feel free to put those in chat, and we'll try to accommodate those requests. So let's go ahead and focus on Saturn and just pay a quick visit to the ringed planet. Now, Saturn is so well known for its ring that the sort of silhouette of the planet with its rings is almost synonymous with astronomy and with science fiction. And as we pull in close, we're kind of coming in above the plane of the solar system so we can see the giant planet. Again, this is a planet that is large enough to contain hundreds of planet Earths, and around it, this brilliant collection of rings. Now, the rings are not solid objects in orbit around. They're not sort of big racetracks that go around Saturn. Instead, you can think of them as many, many tiny moonlets. So while Earth has 1 moon in orbit around it, Saturn has just like bajillions. It has so many little tiny moonlets in orbit around it that we perceive them as this set of rings that were observed by astronomers even hundreds of years ago. And it was only as the observations improved that the nature of the rings became clear. But we have this giant, again, gas planet, gas giant, but not entirely gas, with no solid surface per se. All of these sort of surface features that you can see are actually cloud tops on Saturn. And these giant planets, again, are very different from the terrestrial planets, from the Earth-like planets. But it's these giant planets that actually all have rings around them, with Saturn's rings being sort of the most impressive. So our solar system, just like we could spend an entire program talking about Earth, we could certainly spend an entire program talking about the planets in our solar system. But again, this is a tour of the universe. So let's see how far out we can go and provide a little context for what we're looking at here. So here is, again, our solar system, the orbits of the 8 planets around the sun. The sun is made a little artificially dimmer than the other stars that are being displayed so that we can see the orbits of the planets around it. And what's interesting here when we think about light travel time is that this is we're relatively close together. Now, it takes decades to send our spacecraft out to visit other planets. We've sent Voyager spacecrafts, Pioneer spacecraft, and other spacecraft out to visit different planets in our solar system. But again, light, the fastest thing in the universe, traverses this distance in much less time. I mentioned that the light travel time from Earth to the moon is about 1.5 seconds, sort of a brief pause in conversation. Distance from Earth to the sun, way down here, is about 8 light minutes. So maybe a quick lunch. The distance across the entire solar system, sort of from one side of Neptune's orbit to the other, is about 8 light hours. So you can think of that as like a good night's sleep in terms of light travel time across the solar system. But the nearest star, and coincidentally, it's sort of right behind our solar system right now. The nearest star to our sun is Alpha Centauri. Excuse me. Sorry, I tried to mute the microphone, but it wasn't quick enough. The nearest star to the sun is Alpha Centauri, and that's about 4 light years away. So if you think about the diameter of our solar system as being a good night's sleep, then the distance to the nearest star, 4 light years, is more like a high school or college. So the difference between interplanetary scales and interstellar scales is vastly different. So with that in mind, let's go ahead and actually let me provide one more piece of context here, because we have, as I mentioned, sent our spacecraft out to explore planets. So let me show you the trajectories of 5 of those spacecraft. These are the routes that these 5 sort of fastest spacecraft that we've built, the fastest sort of nuts and bolts objects that we've built and sent out into space, the trajectories that they are taking outside of our solar system. All 5 of these are traveling fast enough to eventually escape the sun's gravity. Basically, they're traveling at escape velocity from the sun. And if you just look at how far, now that you know that this is 8 light hours across, you can estimate how far these various spacecraft have traveled. Now, 2 of these, and let's see, it's a little hard to see here, but let me try to identify them correctly. This is the, I think, Pioneer 10 trajectory out here, Pioneer 11, and then Voyagers 1 and 2. And so those 4 spacecraft were all launched back in the 1970s. So they've been traveling for almost a century. And the 5th trajectory is the New Horizons spacecraft, which was launched in the early aughts. But all of these spacecraft, if you look, have only traveled about as far from Earth as light travels in a single day. And yet the nearest star is about 4 light years away. So even though we've explored a lot of the solar system with our spacecraft, they don't do us any good when it comes to understanding what's going on beyond. So I see a question from Argentina, my favorite celestial body and why? Ooh, well, that's a great question. I find it hard to choose favorites, and I think if you asked me on any given day, I would probably answer differently. But let me keep that in mind as we travel farther away, because I want to point something out when we get far enough from home so that I can show you what one of my favorite objects is. So with that, let's go ahead and put up some markers that indicate where we have found planets around other stars. And I just realized that because we only load the data we need for this program. So I was thinking I could actually take you to one of my favorite objects, but it turns out we don't have it loaded in here. There's one of these circles is encircling a star system called TRAPPIST-1. And TRAPPIST-1 is a very tiny star, kind of reddish star, very dim compared to our own sun, but it has 7 planets in orbit around it, which are all relatively Earth-like. And we suspect that although they are Earth-sized, they're not probably the best place to look for life. However, it's an exciting system that we're really learning to explore. So if you were to ask me today, which you did, I would say TRAPPIST-1 is one of my favorite locations in the universe. And it is one of these little circles that represents a system, a star that has planets in orbit around it. And we know of thousands of these now. And in fact, when we make statistical arguments, we think that basically every star has planets in orbit around it. So it's kind of stunning when you look at the universe from this perspective, because of course, we're interested in thinking about what life would be like outside of our own solar system. We've grown up perhaps watching Star Trek, watching science fiction movies that give us a sense that life could exist out there. And the way that we think life can exist is on the surface of a planet. So knowing where these planets are is deeply interesting. And learning what these planets are like is fascinating to astronomers. So in fact, one of the great things about the TRAPPIST-1 system that I mentioned earlier is that because of the way it's relatively close to us, the way it's positioned in terms of the orbits of the planets being crisscrossing the view that we have of the star, and our ability to make measurements of the TRAPPIST-1 system means that we can figure out a lot about the planets in orbit around that star. And as we find more and more of these, we're able to begin to put together a much more complicated and interesting idea of what planets are like, how these planetary systems form, and what kinds of systems are out there, which in turn helps us think about what life might be out there. Now, the other way that we can look for life is to look for technological signals from life. And actually, we'll have a lecture coming up in April at Morrison Planetarium on just this topic. And one way that we can do that, and the way that we've done it for decades now, is to look for radio signals. So if you can imagine a planet with an intelligent civilization on it that happens to have invented radio like we did about 70 or 80 years ago, they might broadcast their position to the rest of the universe. And basically just like we do. So if I could put up another marker here, this sphere that tucks nicely into our image on screen is a representation of what we've nicknamed it the radiosphere. And the sun and Earth are at the center of this sphere. And it's about 80 light years in diameter. 80 light years in radius, because that's, again, when we essentially invented radio signals that were strong enough to escape Earth's ionosphere, our outer atmosphere. And so this is kind of the outer limit of not the nuts and bolts objects we've sent out into the universe, but the electromagnetic footprint of our species in the universe around us. So if you can imagine, on the one hand, we could look for radio signals from other planets, but we could also imagine that some of these circles, which indicate stars that have planets in orbit around them, maybe there's a civilization on one of those planets that's got its telescopes trained on Earth, making observations. And if they're looking at radio wavelengths, if they're one of these planets inside the sphere, then they'd at least have a chance of detecting signals from us. But if they were outside the radiosphere, even if they had the right technology, even if they were looking back at us, they wouldn't see anything, because this radio signal hasn't had time to reach us here on Earth. So someone asked questions about the data sets for the OpenSpace software that we're using. We do have Gaia data, which Gaia is this amazing survey of literally almost 2 billion stars in our Milky Way galaxy. And it's an incredible data collection that is in OpenSpace. It's not what we're using right now, but it instead we're using an older catalog that's sort of good enough for this application. Plus, Gaia has a lot of data, so it's a little heavy for the software to run, and we try to avoid, because the second part of the question is whether we fill in regions with sort of procedural generation or other kind of sort of fill in gaps. We don't tend to do that. Almost all of the data that you'll see here. Now, I'll mention an exception when we get far enough away, but almost all the data you see here is actual data, actual observations that have been made by various astronomers. So, for example, with the locations of exoplanets, many of those come from NASA's Kepler mission, but some of them also come from ground-based observations. And these catalogs are being built up all the time by many, many astronomers working around the world. So we take what we see as the best data for different sources, and we compile them into this digital universe atlas. And actually, we can add a comment to the American Museum of Natural History Digital Universe website, which lists all of the various sources for the data. And actually, although the current version of OpenSpace does not include detailed information about these data, we're going to be releasing an upcoming sort of manual for the digital universe that will accompany OpenSpace, and that will give you sort of more information than you probably want about all of the data sources for this. Well, let's go ahead and pull away. I'm gonna go ahead and take away our exoplanet locations, the circles representing the stars with planets in orbit around them, and I'm going to pull away now to reveal a very different perspective on the stars around us. We're now moving, we're hundreds of light years from home. So we have traveled in just a few seconds, as the distance that light would take centuries to travel. And we're going to bring up a model, a representation of our Milky Way galaxy. Now, this is a good example of how we do actually sort of fill in data. So all of the star locations you saw were accurate star locations from this Hipparchus catalog of 100,000 some odd stars. But I showed you how far our spacecraft have traveled outside the solar system. No one's traveled this far. But this is a view of our Milky Way galaxy. The center of the galaxy is about 30,000 light years away. And the diameter of the galaxy is around 100,000 light years. So remember, the light travel time, the fastest thing in the universe, light traveling at 300,000 kilometers per second or 186,000 miles per second. It takes more than 100,000 years, basically, to go from one side of the galaxy to the other. To represent the galaxy, we haven't seen what our galaxy looks like from outside, but we've been able to map different parts of the galaxy. For example, the kind of dark regions that you see here are not an absence of stars. They're actually the presence of dust in the galaxy. And we can measure the distances to dust clouds, to molecular clouds. We can figure out the overall structure of the galaxy, and we can see other galaxies, so we have a sense of what our galaxy looks like. To then make a relatively accurate representation in the software, we use a computer model or a computational simulation of galaxies similar to our own, and we represent our own Milky Way galaxy using a single sort of snapshot of what a computer simulation of these galaxies would look like. What's nice about this, and just the reason I kept our radiosphere up, is now you can see, if you can think of that as being sort of our technological history here on Earth, the decades over which we've been broadcasting radio signals out into space. That's sort of our technological footprint in the universe around us. But if you think about 100,000 years, that's roughly the age of our species on the planet. I mean, 100,000 years ago, we hadn't even left Africa. But this begins to become really sort of mind-numbingly big, because now we're talking about distances that I started out as a pause in conversation or a quick lunch or a good night's sleep, or even a high school or college education to the nearest star in terms of light travel time. Now we're talking about the age of our species on the planet. And here in the background of our representation of the Milky Way, you can see some additional sort of faint reddish blobs. Each one of those dots actually represents the location of another galaxy. Now, our Milky Way galaxy contains hundreds of billions of stars, and again, about 100,000 light years from side to side. We have some satellite galaxies here, the Large and Small Magellanic Clouds, and then these other points are more distant galaxies. And there are a couple things I want to point out. First of all, this is all real data. These are measured distances to these galaxies. And what I'd like you to notice is that they're not kind of uniformly distributed in space. They're not just scattered randomly. Instead, they're clumped and clustered together. And this is a really important thing to note because, and something that we've only known for about 40 some odd years, that the universe isn't just sort of uniformly distributed filled with matter. Instead, we have these clumps and clusters, and I'm pulling up additional data sets that are from different observations. But each one of these points represents an individual galaxy. They're color-coded both by the different surveys that were used, as well as as well as in the case of this large data set, sort of the clumpiness of the data, so that more tightly clustered galaxies are color-coded differently from the others. But every one of these points, the main thing is that every one of these points is, in fact, an individual galaxy. And this is where, and you'll notice, I think that the speed with which this live stream updates now kind of slows down. So I'm going to try to make my way very slowly, but in fact very quickly, because we're vastly exceeding the speed of light, away from our location in the center of this swarm of data. You'll notice that there are some kind of regions that are a little better mapped than others, surveys that have gone a little farther out into space with a little more detail. And you'll also notice that there are regions where there aren't many points at all. So when we get to a certain vantage point here, you'll notice that the universe kind of looks like a bow tie or a hourglass, where there are regions that seem to have very few galaxies. And that's not because there are no galaxies there. It's just because those parts of the sky haven't been mapped yet. And so as we begin to fill in more and more galaxy locations, we'll be able to fill in more complete view of the universe around us. But before I take us home, I just want to point out one last thing. And now this is when we really have to grapple with the finite speed of light and the light travel time that I've been mentioning since the beginning of the show. And that is that as we look at our collection of galaxies in this representation, what we're seeing are measurements of light that has traveled to us for literally billions of years. The universe itself is about 13.8 billion years old. And because light travels at a constant and finite speed, when we look out into space, we're looking back in time. And the punchline to this is the mottled kind of reddish image that appears in the background behind or in the distance past all of the galaxies in our data set. And this mottled image is the cosmic microwave background. It is the oldest light in the universe, a baby picture of the universe when the universe was merely a few 100,000 years old, compared to the 13.8 billion years old that it is now. The dark parts correspond to cooler regions. This is kind of a temperature map. The bright parts are warmer, hotter regions, but it's super high contrast. So the dark parts are only one part in 100,000. So 0.00005. I'm sorry, 0.00001 times as cold as the bright parts. Sorry, I don't know if I said that right. But the variation in temperature is about one part in 100,000. And that means that there's a very tiny fluctuation in temperature, which actually also corresponds to a tiny fluctuation in density. And so this baby picture of the universe, when the universe was very young, it was very uniform, but not perfectly uniform. And this slight variation in temperature and density led to the clumping and clustering of matter that became the clusters of galaxies that we see close to home. And so that clumping and clustering of galaxies that I pointed out when we were just beginning to leave the Milky Way behind is a result of this variation in temperature and density that was baked into our universe very, very early on. So, with that thought, and actually one last thing, and that is that one confusing aspect of this is it looks like we're at the center of the universe, because you'll notice that we've kept Earth and the sun at sort of the center the whole time. And that's not the case, in the sense that we don't think that there is a center of the universe, and if there is, we're not at the center of it. That this is that we appear at the center of this image because we're the ones drawing the picture. The map is centered on us because we're the ones making the measurements out into space and back into time. So this is a map of space and time that we're flying through, with the galaxies that we're passing by right now, galaxies that existed in the distant past. And as we eventually make our way back home, we'll be moving back in toward the here and the now. So again, this kind of stresses out the live stream aspect of our platform, but hopefully you'll get a sense here of these hundreds of thousands of galaxies in our data set. And again, each one of these points representing a galaxy that may have hundreds of billions, perhaps even a trillion stars. And so now, as we move in closer, we'll go ahead and start to fade down some of the more distant galaxies in our various data sets until we're just approaching those galaxies relatively close to home. You can see some of the clusters of galaxies in the distance as we travel past them to make our way to our own Milky Way galaxy. And I think I remembered to leave our radiosphere up. So as we approach our Milky Way and we fade down the points representing some of the satellite galaxies, you can still see that little point of light that is in fact our radiosphere, a sphere about 80 light years in radius, centered on our own Earth and Sun. Our electromagnetic footprint, our species' electromagnetic footprint in the universe around us. And as we approach the radiosphere, you can see the 100,000 some odd stars in the Hipparchus data set, not as big as the Gaia data set, but still quite respectable. Let me go ahead and take our radiosphere down as we get closer to home. We'll then pass by the stars nearest the sun inside that radiosphere that represents our outermost electromagnetic influence on the universe around us. We'll make our way to the sun. We're showing it the same brightness as the other stars, but as we get close, we'll dim it down so that we can see the trajectories of those fastest spacecraft that we've sent out into the universe around us. We'll go ahead and fade those down so we have just the orbits of the planets around the sun. We'll make our way in toward the third rock from the sun, our own home planet, Earth. I want to thank you for joining us during today's live stream. Thanks again for visiting us here on Facebook and YouTube. Hope you'll have a chance to visit us in person at the California Academy of Sciences in San Francisco. And in the meantime, have a great day, a great evening, and we'll see you again soon.